To properly understand Gauss's law, we need to understand exactly what electric flux is and how to compute it. So let's begin qualitatively. We can say that electric flux is a measure of the intensity of electric field passing through a given area. And so let's begin by considering a simple surface, namely a square with side lengths s. And so we can imagine something like having an electric field which passes perpendicular to the surface. Or perhaps we might have an electric field which passes at some angle through the surface. And lastly, an electric field which passes through the surface parallel to it. So it is sort of embedded in the surface, and so never actually passes from one side to the other. And suppose that the electric field has equal intensity in each of these cases. We would say that the greatest flux occurs in scenario 1, and there is, in fact, zero flux in scenario 3. So we would say 1 is greater than 2 is greater than 3 for our electric flux. In fact, we can define electric flux in this simplified scenario as phi sub E is equal to E dotted with A, where E vector is, of course, just our electric field. Vector A represents our area with a direction which is perpendicular to our surface. And so in this case, we can now simplify this down to being magnitude of E, magnitude of A, cosine theta. And we can see that given that we have A squared, we would have E S squared cosine theta. In scenario 1, the angle between the electric field and our normal vector to the surface is 0, so that we just get ES squared. In scenario 2, we would need to know some detail about the angle theta right there, and then we'd get ES squared cosine theta. And finally, in scenario 3, our angle in this case, if we draw our normal vector to the surface, our angle is 90, and so our electric flux would be 0. This, of course, is not the form in which flux shows up in Gauss's law, so let's define flux for the more general case. Still not exactly the way it shows up in Gauss's law. We'll say phi E in general is equal to integral E dot dA. And so what does this mean? Again, I'm going to stick with our simple surface, namely a square surface, side length s. And let's begin by defining scalar dA. Scalar dA, with no vector on it, is just a little patch of our surface. And as before, when we introduce the vector, we're going to define its direction as being perpendicular to the surface. And of course, there's some ambiguity there, namely that perpendicular can also go in that direction. That ambiguity will be resolved once we get to Gauss's law proper, but for now, I'll always assume, perpendicular will be to the right when I have a choice between right and left. So there we have it. We've defined dA. And now, if I have an electric field pointing at some angle theta, for a moment, we'll still consider the electric field to be uniform. Let's try to compute this integral. So we're saying that phi E is equal to integral E dot dA. I'm going to begin by trying to get rid of these vectors. And what I'll notice is that the angle is constant between E and dA. And so therefore I can actually evaluate magnitude of E, we'll just write as E, magnitude of dA is just dA, and the angle between them is cosine theta. Moreover, I can say that E is constant for every dA. It does not vary over our surface. Cosine theta also does not vary as we go along our surface. Therefore, I can pull both of those out of our integral to get E cosine theta, integral dA. Of course, integral dA is just our total area. And since we're dealing with a square, our total area is simply S squared. And so there we have it. We've gotten the same results we had with our simplified formulation. Now let's consider something a bit more complicated. Imagine that our surface is still a square. So we're going to consider, I'm just going to rotate our view slightly. So there is our square surface. but located above the center of the square, say a distance y, or let's actually, for simplicity, make that be s over 2, we're going to have a point charge q. And I would like to know the flux through this surface. Now, the good news is, if we now look at this, at first this seems extremely complicated. We would have to do integral E dot dA across our surface. And this time, two things vary. One, our angle. If we look, say, directly below the charge, our field points downwards. But if I were to look, say, at the edge right here, our field points at some angle. So both our angle and our E field vary across the surface, and this looks like a relatively complicated integral to evaluate. Here's the good news. You'll never need to do this integral in AP Physics C at least. And so this is where we're going to introduce Gauss's law. Gauss's law tells us as follows. It says, consider the flux specifically through a closed surface. So integral E dot dA as is, complicated to compute. But let's consider the flux through a closed surface. Now, to begin with, currently we are not dealing with a closed surface. By a closed surface, we mean a sphere, a cube, anything like that. And then Gauss's law tells us if we consider the flux through a closed surface, the circle on my integral indicating that my surface is closed, then integral E dot dA is going to be equal to Q enclosed over epsilon naught, where epsilon is a constant with magnitude 8.85 times 10 to the minus 12. And we call this the vacuum permittivity or the electrical permittivity of space. Importantly, there's a fundamental assumption here that we are dealing with a vacuum. Down the line, when we stop talking about vacuums, we're going to sort of rewrite Gauss's law with just an epsilon in the denominator, and we'll revisit this down the line. So that is what Gauss's law tells us. Now, how is this useful in terms of the problem we just discussed, where we would like to know the flux through r squared with side lengths s due to a point charge, a distance s over 2 around it? Well, what I can do is instead enclose the charge with a cube, now a closed surface, of side length s. And if I do that, note that our charge will be at the center of that cube, which of course is a little hard to draw, but imagine that this is the center. What Gauss's law tells us, without any computation, is that, well, integral E dot dA, the flux, right, so phi E through the entire cube is going to be equal to capital Q over epsilon naught. So that is what we know through Gauss's law. And now we can argue by symmetry. We can say, well, the cube has 6 faces. So phi E through a face, an individual face, will be 1/6 of the flux. So Q over 6 epsilon naught. So all that was just to define what electric flux is. And now that we have a generally good idea of what that is, in the next video, we'll talk about how we can use Gauss's law, not only to find electric flux, but to actually solve for electric fields.